Percent yield. In any experiment where we're producing something using a chemical reaction, we could end up with more product or less product than we expected that we would get. The comparison to the actual measured mass of a product in comparison to the mass predicted from calculation is called the percent yield. So if we take, let's say we did some experiment and we got 2 grams of product X and we thought we should get 5 grams of product X, then the percent yield is 0.4 or 40%. Why wouldn't the percent yield be 100%? Well, just some ideas. If A plus B react to form X, is it possible that X could break back down and form A plus B again? We don't generally deal with this in this class, but of course it's possible. Most reactions that can go in one direction can also go in the backwards direction. And what that means is that we'll get less of the X product than we expected. Not just that, but what if there's an element C that can use up some of the A to produce something called Y? Well, now, because this A gets used up, we won't get as much X as we thought we were going to get. That would be called an alternate reaction pathway. See, this is the pathway we expected A to take, and this is an alternate pathway that we weren't planning on. Some other simple ideas is perhaps the reactants or products have become contaminated. Contaminated products is one example of how a product might produce more than we thought it should, if the mass could be higher than what we predicted. Also, of course, we're always going to have inaccurate measurements and lost or spilled materials in any experiment. So let's just look at a fake situation where this happens to make sure we understand this definition. And then, of course, later we will, in class, do an experiment where we actually see the percent yield of something. 2.5 grams of iron 3 nitrate and 4.2 grams of calcium hydroxide are dissolved in a large volume of water. Precipitate is formed and filtered out. The actual mass of the filtered product is 1 gram. Determine the percent yield. So we got a couple things. They're soluble on their own, but when we mix and match their cation and anions, we're going to come up with an insoluble product. And then using that, we'll be able to determine how much mass of that insoluble product we should have gotten and compare that to the 1 gram that we actually got and come up with a percent yield. So iron nitrate, and it's iron 3 nitrate, plus calcium hydroxide, and it's calcium 2 plus, so that crosses over, iron 3, so that crosses over, to produce calcium nitrate, which would be insoluble, or that's the soluble one, sorry, because it has the nitrate, and iron hydroxide. And it's iron 3, so it crosses over for 3. Now that means I got irons are balanced, calciums are balanced, nitrates, I need 3 and 2 to get them both to 6. And then that's going to mean I need 3 calciums, which means I'm going to need 2 iron hydroxides. And now we're all balanced up properly. Okay, 2.5 grams of this and 4.2 grams of this. Let's see which of us are the limiting reagent. Iron has a mass of 55.85 plus 3 times nitrogen plus 3 oxygens. So that guy is going to be 55.8. 5 plus 3. Yeah, I'm just trying to see. 3 times 16 plus 14 times 3 plus 55.85. 241.85 is the molecular mass of that great big ionic salt. Calcium has a mass of, I think, 40. Yep. 40 plus 2 times oxygen plus a hydrogen. 17 times 2 plus 40 gets me 74 grams per mole. So 2.5 divided by 241.85 gets me 0.0103 moles of, so I'm doing mass divided by molar mass to get the moles of iron nitrate, or if I want to view it as a conversion, for every, I want to convert from grams to moles, so for every 1 mole I have 241.85 grams. Converting from grams to moles, every 1 mole I have 74 grams, so 4.2 divided by 74, 0.0568 moles of this. Obviously I have a lot less of this than I have of that, so this is going to be my limiting reagent, but I could also divide by 2 and divide by 3 to just make sure that's the case. This one worked out to be 0.0189, so that one could do 0.0189 moles of this reaction. And this one was 0.00515, and so obviously this one can only do less of the reaction, and so this was the limiting reagent before I did all this stuff, as predicted. This one is going to run out before that one because this number is smaller. So that means that I'm going to use him to predict future amounts, and I'm basically going to neglect him. The insoluble product I want to predict is this iron hydroxide over here. He is in a 2 to 2 ratio, so that 2 to 2 is the same as 1 to 1, so I don't have to do a mole ratio here. I can just jump over here and get 0.0103 moles of that. I want to know what mass of iron hydroxide I'm going to make. So I need the chemical formula here. 55.85, that's the iron, plus 3 times 16 plus 1. It's going to get me a molar mass of 55.85. 3 times 17 plus 55.85. It's going to get me 106.85 grams per mole. And then if I want to view this as converting this moles, remember I always can use this formula if you prefer, but I want to convert from moles to grams. For every 1 mole I have 106.85 grams. And I got 1.1 grams of product that I expect to be produced. I actually got 1.0 grams. This is my actual, and my theoretical was 1.1 grams. So my percent yield here is going to be pretty good. So since I only thought I was going to get 1.1 gram according to the calculation, and I actually got 1 gram, so I got almost all of it, I would say I had a percent yield of 90.9% here. So almost all. That would be a great experiment.